You go. Yep, all good.
All right. Okay. I hope my screen is visible.
Yep.
Okay, cool. So let me just begin. Okay, so thank you, Bose.X, organizers, uh, for giving me this chance to speak to you all briefly on topics what we do with the radio telescopes. And I'm going to aim at touching on various topics which are individually quite vast. So I'm just going to try and give a flavor of what things are possible with radio telescopes. So to begin with, let me start with a nice animation. Um, this is an animation which takes you to a black hole, as they say. The pictures, images, what you're seeing and we are flying through are real data, color images. Now we are coming up on M87. The red emission is the radio plasma, what we are seeing through radio telescopes, and we are going deeper and deeper in resolution and inside the galaxy and the black hole, towards the black hole. So that was basically the image of the black hole, which successfully was imaged with the Event Horizon Telescope. So that was just a flavor to begin with. Now let's go back a bit. Uh, so hierarchy of the universe. Many of you know this. We start with planets, which are in the solar system. We have stars. We have clusters of stars. We have nearly 100 billion stars in our galaxy. Then we have galaxies, clusters of galaxies, which form superclusters, and then eventually we have the cosmic web. So these are the broad components of our universe, and astronomers study according to their preference and expertise these various objects. Very basics. You have seen the rainbow. We have different wavelengths. I'm going to rush through this because I'm sure you know what a wavelength is, how we measure it, and what it corresponds to. This is the broad electromagnetic spectrum. We have light, as we call it in optical, but it extends far beyond our capable eyes. We need specialized telescopes, instruments, and we have all the way from radio to gamma rays. But in this talk, we are going to focus on the radio aspect. Why? Because I expertise in radio astronomy, but also to emphasize that other wavelengths apart from optical, they give us a whole new other picture and possible physics to do with. So here is a picture of a galaxy in optical as we see, and if we switch on our UV X-ray, telescopes, we can see the same in other wavelength. Same way in gamma rays, infrared. The main advantage for centimeter to meter wavelength uh, uh, radio telescopes is we can observe 24 into 7 or 365 days if the weather is not lightning or hurricanes, but apart from that, we are not affected by the daylight. Now, the signals which we receive on these radio telescopes, they are incredibly faint. So in radio astronomy, we deal with units called as Janskis. It's in honor of Carl Jansky, whose efforts at Bell Labs in the 1920s, 30s led to this discovery of a new window in which we can observe the cosmos. So one Jansky is roughly 10 raised to 26 watts per square meter per hertz. It's a funny unit because the roots of radio astronomy are embedded in antenna and electrical engineering. So to compare them, that one particular unit, we can see how incredibly faint is the signal which we are trying to detect when we compared it to a normal cell phone which we use in our day-to-day lives. And like I said, the principles are of these telescopes is like this. You have a dish, you have signals which is getting focused at the feed, where you have amplifiers which are uh, boosting the signals for us to then process. And using this, we can do different types of observations within radio astronomy. One is called the continuum, where we see the images like we see in optical. We can make radio images. That's called continuum. Then we have spectral, where we can observe one particular emission or absorption lines, like the hydrogen 21 centimeter. Um, and then we have the timing aspect, from which we can observe signals which are repeating, which are coming in pulses. And some of you may have heard of pulsars, so we can observe them. So that's the timing aspect. In this talk, I'll focus on the continuum radio images part only. So this is just a Google map of all the major telescopes, radio telescopes, which are purposed for observing the sky for astronomy purposes. So instead of going about all the telescopes, I'll talk about the pride of Indian astronomy, Giant Meter Wave Radio Telescope, which is in Maharashtra near Pune. And it was commissioned in the late 80s, construction throughout the 90s, and it was the first low frequency radio telescopes to give us detailed maps of the universe. So these are 30 antenna spread across 25 kilometers. Why they are spread across 25 kilometers, why are they so big, I'll come to it. So this is one dish is 45 meters, and trust me, this is really massive. When you stand below it, you get a picture, because the 45 number doesn't really do it justice. But once you're there, so I urge you, when you get a chance, to do visit. And this is a view from a nearby hill of the central array of the GMRT. So you can see it's spread across 25 kilometers with the central concentration. That is where the headquarters of GMRT are. And it's covering 25 kilometers. So at the end, when we combine signals from all these telescopes, it acts like a 125-kilometer dish uh, with the technique of interferometry. And it's needed because I showed you how faint the signals are. So you need a lot more collecting area. That's why we need to make so many of them, because it's not practical to make a 25-kilometer dish naturally. So we employ interferometry to as a substitute. Okay, so this is zooming in basically to the central array which I was talking about, and you have this short baseline which is of 100 meters. If I back up, you can see at the center C6, C9. Now these are crucial for mapping really large structure. The shorter the baselines, the bigger your sensitivity, sorry, the larger your sensitivity to diffuse large structures in radio. So I have to give some time to talk about Professor Govind Swarup, because without him, this wouldn't have been possible, because he's the father of radio astronomy in India. And he's not only built GMRT, but two other telescopes before GMRT in India, and of course was one of the first to propose the square kilometer array, which I'll talk about. So do read up about him. He has many fascinating discoveries and things to his credit. And that's his picture from his celebration from his 90th birthday in NCRA Pune. So yeah, it has produced a lot of interesting research in the past 20 years, GMRT, including several nature science papers. important discoveries. So, coming to what we can study with telescopes like GMRT. These are some broad topics which one can study. Uh, right from exoplanets, which is a recent thing. In the last 10 years, radio has been able to make great strides in exoplanets, stars like pulsars, galaxies, AGN, of course, and clusters of galaxies, and the neutral hydrogen gas, which can be detected with the 21 centimeter. But for the purpose of this talk, I'll focus on these topics. I'll give a flavor of those since we have limited time. And this is, of course, like I said, part of the continuum radio sky, the continuum aspect of the radio astronomy. So a typical radio sky would look like this. The big blob or a shell kind of structure you see near the center is a supernova remnant. Supernova is a remnant of a star which explodes after its lifetime. And rest all the objects which you see are extragalactic in nature. That means they are outside our galaxy, not just outside, but they are quite far. And most of them are supermassive black holes giving out radio jets. Since they are so distant, we can't resolve them with every telescope. We need specialized telescope to resolve their jets. But with a modest resolution, you would see something like these point sources. But each of them have jets. And in the 1960s, it was discovered with the discovery of quasars, which was originally from a follow-up optical observation of a radio source, that these are located at cosmological distances, and that helped push the Big Bang model for cosmology right in the 60s and 70s because with radio and optical you could find objects at very large distances, and the other competing models for cosmology did not account for those, so clearly it favored the Big Bang model. And of course, you may have heard of Penzias and Wilson, them discovering uh, the cosmic microwave background, and that was with a radio telescope operating at much higher frequencies. But yeah, that was basically radio astronomy at play. So, what leads to objects, supermassive black holes, to give out this radio emission? This radio emission is basically comes from this process called the synchrotron process, synchrotron radiation, which is we have charged particles moving at relativistic speeds, giving out in a magnetic field to give out this radiation called synchrotron radiation. It follows a power law. So this is the basic physics which is at play to give out this radio emission, which we detect on the telescope. So if you were to observe a night sky with an optical telescope, a very big optical telescope with very good CCDs and filters, you would see something like this. So the blue bright things, what you see, which are too sparkly, are the foreground stars, and the yellowish, reddish objects which you are seeing, they are distant galaxies. But if you were to put on your radio goggles, you would see this instead of that. You are now seeing extended objects in radio. You're basically seeing jets, the actions of radio jets, which are powered by supermassive black holes. And that's why we need to overlay and actually see that which which optical objects corresponds to this radio source. And that's the way we go about finding and studying these objects. So we characterize them by locating any extended object, which with this one is a radio galaxy, where you see at the center a galaxy seen in optical, the yellowish tinge, which has a supermassive black hole giving out bipolar jets and creating this radio structure. And eventually, if we go deeper in radio with the Event Horizon Telescope, like the video I showed at the start, you will see the photon ring around the black hole, and which is the base of the radio jet. Okay, so like I explained, radio galaxies, these are most numerous in the radio sky, and they are fascinating in themselves to be studied, but they are also used as probes of many astrophysical processes which they contribute to. And they are of course quite big compared to the normal galaxies, because a Milky Way like galaxy is about 200,000 light years, or 30 kiloparsec or so. But when you have radio galaxies, they grow much more, 100 or even 1,000 times the size of Milky Way. And like I said, you have okay, let me just play this quickly. You have this black hole at the center, which is giving out this jet. So basically, the processes happening there are it the spinning black hole is accreting matter from the surrounding gas, dust, and it's spinning quite rapidly to make this accretion disk, and making a magnetized accretion disk, which is uh, funneling these charged particles and creating this jet, which we are observing as radio galaxies eventually. This is another simulation of the same, so I'll skip this. And you can see the size comparison of these massive objects, how they fare compared to other famous objects which you have seen in optical. And these are all radio images of different radio galaxies. You can see they comes in all shapes and sizes, and they're governed by not only the power of the black hole, but also the surrounding medium in which they are growing, because that at times dictates their shape. So by studying their shapes, we can actually comment or decipher about the environment they are growing in. So you have this gallery now of various shapes. Now each of these shapes, they do have a little funny name, but each have a very significant contribution in understanding what governs their size and growth, and also the environment. So the wide angle tailed, which have a U or a C shaped shape, uh, they are mostly associated to galaxy clusters. They are basically the host galaxy is moving inwards, falling towards the center of a galaxy clusters where the massive gravitational potential is lying. So the radio plasma is bent as the host galaxy, where the black hole is giving jet, is moving towards the center. And same with the narrow angle tail, which are moving much faster than the VATs. X-shaped are the ones which are most likely hosting supermassive black holes, or more complex physics of interacting with the interstellar medium. And then we have the restarted double radio galaxies and eventually giants, which are the biggest single structures in the universe. And like I showed you at the beginning, you have uh, sources which can be studied with multiple telescope, because each of them tells us a new story. So what you see here in the at the top is Cygnus A. In red, you see the radio jet and the radio lobes which it creates. The yellowish objects, what you're seeing, are the optical image of galaxies, and the blue is hot X-ray gas, okay, which are seen by Chandra telescope. So you can see when the radio jets is passing through this or piercing through this hot X-ray gas in a galaxy cluster, it is making bubbles or cavity. And by studying the properties of these cavities, we actually uh, 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 estimate the power of the jet, and that comes to about 10 raised to 45 arc per second, which is really massive. So you need multi-wavelength data to at this precision to study and understand these objects. And the Uh, Talking about giants, it's the definition for giants is megaparsec scale, and 1 megaparsec is around 33 Milky Way galaxies stacked in a line. And this is how the size comparison looks. You have objects now all the way to 5 and beyond, 5 megaparsec and beyond, and our Milky Way is not even visible here. So these are very massive objects which have uh, different purposes too, which I'll get to later part of the talk. Okay, now that I've given you a flavor of what is possible to be observed briefly, let's back up a bit and go to some techniques. So about the interferometry. When you have a single dish, its resolution is determined by the size of the dish, because the resolution theta is lambda over d. Lambda is the observing wavelength or frequency, and d is the size of the dish. So, like I said, it's not practical to make a 25-kilometer dish. So that's why we employ interferometer, where the longest baseline, which is the distance between two telescopes in an interferometer, determines the resolution of the images you're going to produce, where the D is not the dish size of the dish, but it's the size of the entire interferometer, the longest baseline. And this is one such telescope, the Very Large Array in the United States. The advantage of this telescope over other telescope is these massive dishes can be moved, meaning you see those dark lines. These are basically railway tracks. So every few months they pick up the whole dish, put it on the railway track, and transport it to greater distances. Now, why do they do that? They do that to map radio galaxies at different sensitivities and resolution. So I told you about the shortest baseline concept. The shorter the baseline between two elements in an interferometer, you have more sensitivity to detect diffuse and larger structure. So when they want to detect such a structure, they bring their all telescopes as close as possible. And when they want to detect at very high resolution, they spread it out. So the maximum they can go in the A array is 36 kilometers. And the advantage is when you have very short configuration, when all the telescopes are compact, you see something like this. You see a radio galaxy, but it's faint. It's like you're not wearing your specs. You see a blurry, nothing sharp. We don't understand much. So then they change the array. They make a higher resolution image. Now you can see a dot at the center, which is where the core of the galaxy is, the host galaxy, and you can start seeing the jets. But if you go more in resolution, higher in resolution, you see more structures. You see some backflows, you see some shocks. And if you go more finer, you see more structures within the structures. And that is the advantage. And eventually you can then combine and make a beautiful image like this. Now here you have bipolar jets clearly seen coming out from the black hole at the center and creating this massive structure, which at times can grow to megaparsec scales. So that was the importance of resolution, but I can tell you more that if you have, for example, a radio image with just 45 arcsecond, you'll see a blob. You go higher in resolution. When I say higher, it means the lower value in number. You see a tail structure. But if you go even further, you see that it's not one but two structures altogether. So that's why we need to image the radio sky not at just one frequency or one resolution, but at multiple resolutions to really nail down that, okay, what is really happening here. And the same applies when you're imaging objects which are close by to us, that is within our galaxy. So what you're seeing are supernova shells, which can at times be misleading for us. But when you image them at the higher resolution, so the bottom image is high resolution, you can actually see the shock fronts of a supernova shell in radio. And as I promised, the M87, coming back to it, how one goes about it. So you can see the resolution and sensitivities at play here, all the way from A to F. So you have the M87 is actually quite massive, but if you keep on resolving it, the centralmost part, you're going to see more finer aspects of the jets, and eventually in F you see the base of the radio jet. And that all is possible with a telescope whose baseline is not just 36 kilometers, but almost the size of the Earth, because you need to spread out telescopes across the globe. So here we are talking of almost 3 to 4,000 kilometers baseline. So it was incredibly hard to do, because interferometry was championed in 70s, but to champion it to such length, such large distances, it took almost 50 years, because it is incredibly hard. So these are some telescopes which are doing these observations at very high frequencies, so that you're able to go down to micro arc second resolutions. The images I showed you before were of sub arc second or arc second, but with to image event horizon scales, you need to go to micro arc second, and that's why not only you need to have a longer baseline, but you also need to go to higher frequencies, because it's theta equal to lambda by d, so you need your lambda as small as possible. Then again, coming back to the importance of multi-wavelength, because just a radio image is not going to give you the full picture. You need to localize that what is the host galaxy. So here you see the importance. The red is basically the host galaxy. You have jets, but the bottom jet is bent because the host galaxy is moving in the southward direction, causing this tail-like structure to be formed. Now coming to observing at multiple frequencies in radio. So this is the same Hercules A radio galaxy which I showed you, but now you're seeing images at different frequencies or different wavelengths. So at the top you're seeing on the left in blue is the very low frequency or big wavelength. It's like almost 2 meters. Middle you're seeing at 20 centimeters, and then if you're at the bottom you're seeing almost 5 to 6 centimeter wavelength. Now, what happens when you combine these images? You can study their spectral nature, because, like I told you, these follow power law. This radio emission is basically coming from synchrotron radiation, which follow power law. And when we combine these images and make a spectral index map, you can see the plots on the right. Now, we have from synchrotron theory, we know that the flatter the spectrum, though, so by flatter, I mean values greater than minus 0.8, and anything below is steeper. Now, flat and steep, these are two concepts. Now, flat is telling us that the emission is continuously being fed by the jet. It is newer, and steeper indicates that the emission is older. A significant time has elapsed, and there is a lot of radiative cooling happening there, which is why they are coming out to be older. So, by studying them at various frequencies, we can actually uh, understand their ages, how long they have been active for, and then using that we can comment on their duty cycle, about how efficient the black hole is at giving out jets, and over what period of time. So before these objects are studied, we need to even find them. So we make a big map of the sky at coarser resolution, which looks something like this. And then we go about looking for interesting objects, because we can't study all the point sources one by one. So we need to cherry pick some objects which look exceptionally interesting. So the ones who in the audience were very attentive, they must have spotted some peculiar object towards the right side, which is now getting zoomed in. It shows a very peculiar structure, and that's what happened to me when I was doing these searches. Once we localize them, we try to look at its optical image, that how the optical counterpart of these images look, and or firstly we also need to determine whether these are single object or multiple objects which are coming out to be together due to poor resolution. So we tried to do that. We found the optical galaxy at one particular peak, but this was not telling us enough. So once we have identified, we need to do follow-up observations to get higher resolution images, and that's what I tried to do. We have to write a proposal to the telescope saying the merits that okay, we want to observe these objects because we can probe this astrophysics, and we need to tell them that we need to observe for so much time so as to reach this much sensitivity, basically exposure. The fainter the object, you need to observe for longer periods of time. And then there is a committee which sits every 6 months, evaluates the proposal, and then if it is good enough, they give you time. Fortunately, I managed to do it. I went to GMRT to observe this telescope, not the telescope, but also the object. And if you're lucky, you'll see something like this during your observations. What is this showing is basically on the x-axis is the frequency and y-axis is the power of your radio signals. And the spikes you see are RFI, which are there. You can't help it. A diesel-based tractor can give out this kind of RFI, mobile phones, lot of things which are there near the fields of GMRT. So, but we have learned to deal with it. We have sophisticated packages to remove this RFI, radio frequency interference. But at times you are handed over this. In the earlier plot, you had hints of RFI in data, but here you have hints of data in RFI. And if you're unlucky, this can happen to you. Fortunately, this didn't happen to me, but it happened to my other colleague. Anyways, coming back to the image, once you process the image, interferometric image, you see the high resolution image like this. So those blobs now have resolved into jets and more epicular structures. And if you go to higher resolution, you can clearly see 300 kiloparsec jet with the core and everything imaged. But we found more peculiar stuff, which came out to be this, which is plasma instability over 100 kiloparsec, kink kind of structure. So 100 kiloparsec is basically 3 Milky Way galaxies in a line. So these are plasma instabilities which are occurring due to it, some shocks and interaction with the medium, because basically this is fluid plasma, but it is occurring because it's in a dense galaxy cluster as well. So these are all conjectures at the moment. We need to model it further and talk to theoreticians and simulation to produce this to understand what is really happening. Okay, now that I'm running out of time, I'll quickly jump. So I've talked about galaxies, AGNs, radio galaxies. I'll talk about galaxy clusters. So what you're seeing is two galaxy clusters, which are actually merging. Yes, galaxy clusters also merge to become bigger structures. And what happens when two galaxy clusters merge is they give out these massive shocks, okay, which are only seen in radio. So these are called relics, radio relics, which occur due to two galaxy clusters merging over lot of giga years, and the plasma is amplified and the shocks are presented in this way. Okay, I'm going to skip this. I'm going to come to something exciting. What we can do in with the radio telescopes and radio data is now start asking questions about more bigger things, the cosmic web itself. This is what I tried to do with one of my collaborators. Basically, this is Faraday rotation in astrophysical setting. So I think you guys might have studied for what is Faraday rotation. So you have a polarized light. When it passes through a magneto-ionized medium, the plane of its polarization changes, and we can detect that depending on the strength of the magnetic field and the size of the size of the whole magneto-ionic medium. So this is what we tried to do. We took a supercluster and we tried to find a polarized radio source behind it, and then observed the rotation it is causing. So basically, you have the radio galaxy, which is giving out polarized radio light traveling through the supercluster, and the magneto-ionic medium inside the supercluster is rotating the plane of their polarization, which we are detecting on Earth. And basically, with this shift, we can actually estimate the magnetic field which is prevalent in the supercluster itself, and we got it around sub-micro Gauss. So this is very hard to do because there are not too many polarized radio sources in the sky, at least to the sensitivity with which our current telescopes are operating. And then second is localizing them exactly behind a supercluster or a cluster is quite tricky. And like I said, so here is a proof of using them as probes. The other is a recent discovery which appeared in Nature of for giant radio galaxies. They found a 7 megaparsec big giant, and which is unimaginable because the record before that was for 5 megaparsec, and most giants are around 1 to 2 megaparsec. 7 is beyond galaxy clusters because a normal galaxy cluster is about 4 to 5 megaparsec, but here we are talking of 7 megaparsec. So it is thought that this is growing into voids. Now, just by their growth into voids, we can now probe voids. So this becomes the possible probes of voids, okay? And that too at a redshift of 0.9, which is really distant. So this is all going to get more exciting with the square kilometer array, which is about to start in about 2 years from now. The first slide, the commissioning data is already here, and it's going to be a very exciting time. So this is just a small video because it's spread across 2 continents, this telescope, and operating at various frequencies with state-of-the-art instruments and electronics. I'll skip this. Okay, wait. So this is going to be great because it's going to cover a lot of area. So more collecting area, more power to detect fainter signals. It's going to uh, it has already done a lot of infrastructure development and actually patented in process. A lot of patents have been generated. A technology which is not only aiding astronomy but other aspects of human life. Okay, I'm going to skip this. Time is less, but it will bring us a lot of challenges actually, because it's going to generate petabytes of data per second, uh, and it's going to be a nightmare. But we are trying to address these things because we not only have to think about its storage but processing it, and we absolutely will need supercomputers. Already, the current LOFA data needs supercomputers. Transferring such data will be a nightmare, and more importantly, it's going to generate deepest radio images ever, uh, and it's going to be very challenging to catalog all the sources, characterize them, and it's going to be humanly impossible. So, how do we expedite these findings? We need to put more manpower. We need enthusiastic, intelligent people like people in this audience to join this effort. We need to employ automated algorithms, machine learning, and then there are some ongoing efforts with citizen science as well, with the Radio Galaxy Zoo and Ride at Home, which is an Indian-based initiative. So the future looks quite promising with all these telescopes which are going to come in the next few years. JWST is already here, and but it's going to keep revolutionizing in the next couple of years as well. So hence I've put it in this slide because the results from it have been mind-boggling, and equally these will be great with SK and other telescopes. So I'll stop with this. That it's fascinating. A lot of objects in this universe to be studied, and yeah, I hope you'll consider joining this effort. Thank you.
All right. Let's just thank the speaker. I'll just clap from my side. Thank you, Pratik, for this nice talk. So as people might know that Pratik is like an expert on the radio side of the universe. So we're happy to have questions. So if someone wants to start, feel free.
So just a quick question. Well, thank you, Pratik. I guess when you were doing your PhD in Ayuka, I was there interning. So I guess we already met, and pleasure to meet you again. It was interesting talk. And you mentioned at some point the void, probing the void. So what do we expect from this void? Like, what exactly is there?
So voids are super underdense regions of the universe. You have galaxy clusters, you have filaments, and
Okay.
we have then the voids. Now voids are very interesting because voids are supposed to have a magnetic field which is pristine. Okay,
Mhm.
they are supposed to be underdense, so there is not much pollution from other astrophysical processes there. And by pristine, I mean you have magnetic fields and other conditions all the way from inflation. That is
Okay.
the theory.
Mhm.
So studying them gives us more insight into the initial conditions of the universe by constraining various parameters like the magnetic field, the sizes, the underdensity, etc.
Okay, I see. Thank you.
Okay. Akash.
I think I'm muted.
I can go first. He I think raised his hand prior to. Okay. S- Okay. Okay, then I will ask. And so with this new VLBI and the interferometers, can you is it possible to resolve stars already in galaxies like M87, which are far away, or?
Um, I think so, yeah. But for that, you don't need radio telescope. You can do that with JWST or
Okay.
Hubble telescope, Hubble
Mhm.
Space Telescope. Yeah.
And second question was, what about chemistry or molecular signatures in this um, faraway galaxies? Are there already some
Lot of it,
in,
lot of it.
okay,
There has been a lot of study in that, especially with JWST.
okay,
Yeah, even the recent discovery from Cambridge.
yeah,
Uh,
yeah,
yeah, so that's possible with JWST. Basically, you basically take light and pass it through a spectrum. Basically, they get a spectrum.
yeah,
Yeah. So, but in radio, of course, with resolution you can resolve down, but eventually you'll have to do spectroscopy only.
yeah, yeah,
Yeah.
yeah. Okay, thanks.
Uh, Hi, Pratik. Very
Right.
nice talk.
Thank
Uh,
you.
I have a basic question. So, if we look at a patch of the sky and uh, jets will not be in large number. So, I understand that the jets are collimated and it depends upon the black hole spin. So, what does it tell us? Not all black holes are like highly spinning, or does the length of the jet does it have any correlation with the spin of the black hole or
That's
higher?
open end. Yeah, currently that's an open-ended question. That's why people like me are employed. We are trying to understand this.
Okay.
Uh, there are so okay. Let me go back to this particular image just to Now, all the points which you see here, these are unresolved jets. All these are unresolved jets. So we can't say that there are not many. Okay, they are quite plenty. It's just that our ability to resolve them and study is not there currently. Resolve everything, because you need to then you need to study the whole radio sky at sub-arc second or micro-arc second. But also we have to keep in mind that when we go very higher in resolution, you lose out flux. Okay, so you need a combination of telescopes to not only map them at very high resolutions, but also not lose out the flux, because that's where our so something like this. Okay, you need finer structures to be mapped.
So how far in redshift are they? Are these galaxies?
Okay, so radio galaxies, the farthest radio quasar has been up to redshift 7, 7.2, I think. And in terms of jets, I think 6 redshift of 6.5 has been mapped with very long baseline interferometer.
So the images that are already being detected with high resolution. So were they able to measure the spin of the black hole?
No, you can't. I mean, there is no direct way to measure the spin of the black hole apart from X-ray observations. Okay, in radio you can't measure the spin. The Event Horizon Telescope, they have quoted the spin of M87, but that's based on a model. It's a very indirect way of thing. To measure the spin of a black hole directly, you need X-ray emission coming out from the black hole. It has to be reasonably close to us so that our modest X-ray telescope can resolve, and it has to give out a particular line. Okay, and that line we will observe. Since it is rotating very fast, we will observe the double hump profile. Okay, from that we can then determine the spin of the black hole, and that has been successful in handful cases.
Okay.
Yeah.
Thanks.
I just have a follow-up question. So, is this the spin, like the angular momentum of the black hole we're talking about, right?
Yes, in a way.
Good. We have question from Satyam Singh in the chat. Satyam, would you like to speak if you want?
I think his audio connection is. We can read out the question.
Okay, I'll just read out the question. So the first question, he has two questions. The first is, does the Earth's atmosphere affect radio astronomy observations? If yes, how?
Yes. So Earth's atmosphere, in a way, does affect radio astronomy observations. So we have ionosphere way above the Earth, about 100 kilometers, if I'm not wrong, where there is denser medium, and these are patches. These are not uniformly surrounding the Earth or engulfing the Earth. And the longer the wavelength of observation, the higher they can distort the radio waves before they come to our telescope. Okay, so basically what you see in the optical twinkling of the sky, twinkling of the stars, that is the kind of effect we will see for low frequency radio waves. It doesn't affect that much for higher frequency or smaller wavelength radio emission coming from outer sky.
Okay, there's another question. So why are radio telescopes often built in remote locations?
Well, like I said, okay, so some of these telescopes, the ones operating at very high frequency, 100 gigahertz and above, they are affected by the water vapor, because 100 gigahertz corresponds to almost millimeter wavelength. Okay, so the waves are going to get affected by the water vapor, which is there in the atmosphere. So you need to go at a very high altitude to beat that. Okay, so those are telescopes above 100 gigahertz. That's why they need to go remote and at the top of a mountain. And then other telescopes, anyways, need to be away from the city for tackling the RFI, radio frequency interference, because I showed you that nightmare plot, right? So, yeah. It's radio light pollution, to get away from radio light pollution in a way. I think there is Nishchay who is raised his hand.
Yeah, could you please? Yeah.
Yeah. Hope my voice is pretty clear.
Yep.
Yep. Okay. Yeah. Thank you. Thank you, Dr. Pratik, for your wonderful section. I have a question that is inspired from Ankul's questions indeed. When you were talking about, when one of your slides also mentioned about that stated when a black hole ejects jets, you had also shown few images of that jet, and you had talked about voids on that jets when we are talking about the radio frequency jets. So could you please elaborate on why are these voids and humps observed when we talk about when we consider the radio aspect of it, radio frequency aspect of that?
Firstly, voids and radio galaxies, they are very two different aspects. Okay. Radio galaxies are galaxies which have active galactic nuclei, a black hole at the center giving out these jets. Now, these jets make these radio galaxies, okay? And these can grow to 100 kiloparsec or megaparsec. So they can grow into any medium that is surrounding them, okay? Where you have, like you see in this uh, artist sketch, these are dense medium. Okay, these are filamentary structures in the cosmic web. Okay, let me show you. This is the cosmic web. Okay, so this looks like what satellite images of our cities show, right? These are cities, these are forests, right? So this is where galaxy clusters and filaments are present, in which galaxies are there, and galaxies are the ones hosting black holes giving out these jets. But sometimes these jets are so big, and by the way, the scales here are of 10 megaparsec and big. And then if there are one or two galaxies like these here, and they happen to give out jets, they can grow into these voids. And this is a void. Void is not an absolute absence of matter, it is the underdensity of matter in universe. Okay. So we are using radio galaxies as probes of voids. Does that answer your question?
Yes, sir, absolutely. Thank you.
Great. If people have more, okay, Uncle. Yeah.
Noted.
I think you go first, what you're about to say.
I was saying that I have a question.
Yeah, sure, please.
Okay. So you talked about the remnant of the dark matter halo colliding. Was it something like that?
Well, yeah, there is yeah.
So
There is dark matter here. Yes, of course.
yes, I would expect. So is that the case that when halos collide, there would also leads to like merger, or
Shocks.
is this the case that they will just cross through?
The baryonic visible matter will not completely cross through.
Okay.
There will be some parts which will be colliding, creating these shocks. But dark matter will most likely just go through, which we see
Okay.
here in a way. Yeah.
Okay, perfect.
Yeah, and there is a Japanese there are Japanese authors who have given out gravitational waves coming out from galaxy clusters. Okay, you should check that out. Of course, those cannot be observed with any of the future missions also, because they are like kiloparsec long gravitational waves coming out. Yeah, but there have been studies.
Perfect. Great. Yeah, I don't have any more questions. If just the last call for questions, if people want to ask anything else.
I have a question, everyone. Since Pratik, many of from audience, I guess some bachelor master students, what do you think, like how they can be kind of contributing to this effort as still being maybe remotely, or if they are still in the courses and during the academic year, what kind of projects or something which can be formulated, or something, some study materials or some tools you would like to maybe introduce?
Sure. So first of all, do all these extra things only when you have ample time after thoroughly doing your coursework, a master's or a bachelor's, and you have dedicated times in summer and vacation times, so you can do projects with various professors either remotely or in person. But don't let yourself get exploited by any professors by doing some menial work. So be careful, don't be desperate, because not all people are nice out there, so be very careful. My emphasis first would be to undergrads and postgrads would be, if you want to come into this research in astrophysics or any aspects of physics, be very thorough with your fundamentals, with your concepts. You will not get time to boost those foundations later on once you start actual research. So undergrad and postgrad is the best time to do as much as wide physics you can do and get strong. Coming to what they can do when they have ample time to learn more aspects of research is uh, do courses like you guys suggested on your Bose.X platform. Apart from that, on YouTube, there is a lot of resources on various topics. Of course, books are there. You can reach out to good professors or good researchers, not only in India for projects. In-person project is of course much better. If you get that opportunity, that's great. If you can't, then you can reach out to various professors around the world who are okay with doing online mentoring. So that is one broad aspect. But uh, most astronomers nowadays are dealing with a lot of data. So naturally, we need manpower. So any astronomer dealing with a lot of data, and you coming to them with your data analysis skills or skill set to learn new things faster, I think they will welcome you. So yeah, it's just identifying what you like to do and then reaching out. And if you're not sure what you like to do, I think I would suggest go through some resources. Places like RRI, IUCA, they already have a lot of good resources on YouTube, like complete introduction to astronomy coursework. Even the ASI, Astronomical Society of India, has a nice basic course in aspects of astrophysics. I think you could start, even on NPTEL, there will be more in-depth courses. And then after going through that, you may get your calling. Okay. Does
Yeah,
that?
absolutely well said. Thank you.
Yeah. Yeah.
Might be probably helpful for others. Yes, yeah, there's one more question.
Yep, Harish had a question.
Yeah, hi Pratik. I
Hi.
don't know if you already covered. So with radio data, will we be able to detect like these rogue black holes, like isolated black holes that are drifting in the intergalactic medium?
Well, if they are giving out jets, sure. If they're not giving out jets, then we can't,
Okay,
because
yeah. I mean, theoretically, these black holes doesn't have that much things to interact. So they will have like very weak jets, but so it will depend upon the sensitivity of our telescopes to detect.
if you're talking about primordial black holes, then
No, no. And
okay.
not the primordial ones, but the normal black holes, like the ones that form from the star products. But it will be like isolated, will not have that much
Yeah.
intergalactic matter to interact with. So it will be give out very weak radio signals, but it will depend upon our radio sensitivity to detect it.
No, okay. So there is a way to detect them indirectly, and there have been few cases. You have a supermassive black hole. You have giving out radio jets, making a radio galaxies, but at times their jets are twisted and turned, and that is conjectured that there is a nearby black hole which is not radio loud, which is not giving out radio signals, but it is affecting the other black hole, which is then they are trying to coalesce, and then that is reflected in the morphology of the radio jets. So that's an indirect way. So you can look at OJ 287,
Okay.
which is doing such a thing. So there are indirect ways like this. Yeah.
Thanks.
Shashwat, I think you are muted. Yeah.
Yeah, I was saying thank you, Pratik.
Welcome.
Again, I think way past the hour. So if we have questions, I've shared your LinkedIn to people. Maybe they will reach out to you with questions if they have any. And I will let the Zoom open for 10 more minutes. If people have questions about Bose.X, we are happy to just take those questions. And yep, thank you again.
All right. Thank you for having me. Good talking to you all and interesting questions.
Thank
So
you.
yeah.
See you.
Okay. See you later. Bye bye.
Bye-bye.
Bye. Thank you.